Hello and welcome to the April webinar from the IEA Clean Coal Centre. My name is Deborah Adams and I'm Studies Manager here at our office in London. We do a webinar each month and they're always based on our technical reports which are available from our website www.iea-coal.org. Residents of member countries and employees of sponsoring organisations can download our reports at no charge after a one-off registration. All this information can be found on our website. The subject for today's webinar is Next Generation Carbon Capture Technologies for Coal-Fired Power Plants. The report on this topic by Toby Lockwood has been out in draft for a while and should be published in the next week or so. If you have any questions during the talk, please use the Ask a Question box at the top of your screen and add your email address as well so that if we run out of time, Toby can then send you a fuller answer. Okay, over to you, Toby.
Thank you, Deborah, and hello, everyone. I'm going to move straight on with the first slide. So, to review the current status of power plant CCS, with the opening of a carbon capture plant on 120 megawatt unit at Boundary Dam Power Plant in Canada in October 2014, CCS was applied to a power plant for the first time. Two other power generation projects are currently under construction in the US and scheduled to start this year or early 2017. Like Boundary Dam, the Petronova project, the existing WA Parish power plant in Texas, uses an amine-based post-combustion process, which has emerged as the leading technology for most forms of carbon capture. On the other hand, the Kemper County project in Mississippi has involved the construction of a new integrated gasification combined cycle power plant, or IGCC, which will be equipped with pre-combustion CO2 capture using a commercial solvent. Whilst a few other projects at advanced stages of planning are still active worldwide, both Europe and the US have seen numerous high-profile cancellations of CCS power projects, and the technology is yet to be deployed at the necessary rate. It should be noted that the successful North American projects have several features in common which help favour CCS, including the availability of a low-cost, long-term coal supply, the sale of CO2 for enhanced oil recovery, national legislation which effectively prohibits new coal plant without CCS, and local utilities which may have little or no competition. So carbon capture is a commercial and technically viable technology for coal power, but current forms of the technology appear prohibitively costly in all but the most favourable circumstances. Current estimates by the US NETL put the cost of electricity from a coal plant with amine-based capture at over 70% greater than an unabated plant, with similar figures for IGCC pre-combustion. This can also be expressed as a cost of $60 to $90 per tonne of CO2 captured. This cost is in large part associated with the significant energy penalty imposed by the capture process, which can reduce power plant efficiency by up to a third, requiring a much larger plant to generate the same output. Of course, the capture plant itself also has capital and operating costs. Fortunately, this energy penalty is not a fundamental limitation. It is informative to look at the theoretical minimum energy required for gas separations at the heart of the three main capture strategies, that is CO2 from nitrogen for post-combustion capture, CO2 from hydrogen for pre-combustion capture, and oxygen from air and Oxyfuel capture. Current processes are far from approaching these theoretical limits, and the favourable conditions of pre-combustion capture mean there is even more room for improvement. However, it should be noted that at least half of the minimum energy is for compressing the CO2 to pipeline pressures, and is difficult to improve on, as it's based on quite well-established compressor technologies. So this potential has led several countries to fund research programs into developing better capture technologies with reduced energy consumption and cost. Most notably, the United States has set out a timeline for new technologies with cost targets using the cost of electricity and cost per tonne of CO2 as measures of their relative performance. The EU has funded similar programs aiming at 15 euros per tonne, and other advanced CO2 capture development is taking place in Australia, Korea, Japan and China. Most researchers required new technologies to be capable of capturing 80 to 90% of the carbon emitted, producing CO2 at over 95% purity, which is suitable for pipeline transportation. New capture technologies being developed can generally be grouped into the traditional approaches of post-combustion, pre-combustion and Oxyfuel, although chemical looping is often considered a unique approach. Usually there is a gas separation at the heart of any process, which can be carried out by liquid solvents, solid sorbents, membranes, or other means such as cooling to the CO2 sublimation point. Many such processes are already used in other commercial gas separations, but can be challenged by processing the huge volumes of gas generated by coal power plants. Although highly efficient capture processes can often be achieved with sufficiently complex equipment or costly materials, the cost of the capture process itself can quickly start to outweigh energetic gains, particularly given the necessary scale of the CO2 plant. So most people should be familiar with the well-established process using solvents based on the range of organic molecules known as amines, which chemically react with CO2. The CO2 absorption process takes place in an absorber column producing a CO2-rich liquid which is heated with steam in a stripper column to release pure CO2 and regenerate the solvent. The considerable energy consumption of this process is related to the strong bond formed with the CO2 as well as the high water content of the solvent, which adds to the thermal mass to be heated. Another issue is the tendency for these molecules to degrade under operating conditions, producing environmentally hazardous waste and emissions. Research into improved solvents is therefore focused on optimizing the strength of the interaction with CO2, reducing the water content, and using more benign chemicals. So this study has not focused on improvements to amine solvents or optimization of the absorption process, although both have seen steady progress. Instead, I've looked at more novel solvent systems which aim to achieve dramatic improvements in energy or cost. Precipitating solvents and liquid phase change solvents have been widely studied by several research groups and companies. These both essentially aim to reduce the thermal mass of the regenerated solvent by separating out a smaller mass of CO2-rich solid or liquid from the rest of the solvent. Some notable projects include GE's precipitating solvent based on aminosilicones and a liquid phase change solvent developed by IFP Energy Nouvelle in France. These are both at the bench scale currently. Ionic liquids are a range of organic salts which allow the regeneration energy to be tuned and optimized, but they generally feature high cost and excessive viscosity. Current interest is focused on blending them with other solvents, with US company Ion Engineering promising a particularly low-cost system. Some interesting lab-scale work at the Lawrence Livermore National Laboratory has looked at improving the operational performance of many of these advanced solvents by encapsulating them in gas-permeable polymer shells. These will be contacted with flue gas in a fluidised bed reactor, presenting a very large liquid gas contact area. So I'm going to focus on enzyme-activated solvents here. Carbonic anhydrase is an enzyme which regulates CO2 levels in most organisms by catalysing the hydration of CO2 to a soluble acid or vice versa. As this dissolution is the rate-limiting step in aqueous capture processes, the enzyme has been used to accelerate the desorption and absorption process for solvents which usually react too slowly, such as potassium carbonate, which is low cost and environmentally benign. However, natural enzymes are not stable under industrial conditions, so more thermally resistant variants of carbonic anhydrase have been developed by several companies. For instance, Canadian company CO2 Solutions have developed a capture process using potassium carbonate with a free-flowing enzyme and operate a pilot plant able to capture 10 tons of CO2 per day. Due to the presence of enzyme in the stripper, hot water can be used instead of steam for solvent regeneration. An alternative to solvents for post-combustion capture is the use of high surface area solid materials which preferentially absorb CO2 over nitrogen, encompassing activated carbons, zeolites, metal organic frameworks, silica-sported amines and others. These sorbent materials can theoretically offer lower energy requirements and higher CO2 capacities than solvent systems. Once the CO2 has been absorbed, it can be released either by lowering the pressure, known as vacuum swing absorption, or heating, known as a temperature swing. Although several larger pilots have been built using vacuum or pressure swings, most current research is investigating the use of temperature swing processes which avoid energetically demanding vacuum pumping. A key issue for solid systems is that heat transfer is much less efficient than in liquid systems, and scale up to large gas volumes may therefore be challenging. The simplest form of reactor for solid absorbers is a packed bed of sorbent particles with several reactors operating in sequence to achieve a semi-continuous process. However, this is not ideal for large flue gas volumes which require rapid throughput and therefore rapid heating and cooling for each cycle of the temperature swing process. Using a rationally structured sorbent, often formed as an extruded monolith, is an increasingly popular means of optimizing the reactor to have a reduced pressure drop and fast heat transfer. Developed by Inventus for Loxotherm, is a unique capture process based on a rotary heat exchanger in which a structured carbon sorbent rotates between regions where CO2 absorption takes place and where steam is applied for desorption. A key advantage is that the heat released by CO2 absorption is retained and used to assist in the heating step. With the 25 megawatts pilot, I think, planned with utility NRG in the US, Inventus are targeting a capture cost of $30 per tonne, including compression. So another means of contacting flue gas with solids is the use of moving or fluidised beds in which the sorbent particles move between the reactors for CO2 absorption and desorption. This is a similar fashion to solvent processes. The relatively efficient heat transfer in these reactors allow the use of highly selective sorbents which chemically react with CO2, such as amines supported on silica or metal carbonates. The largest solid sorbent pilot in the world is a 10 megawatt fluidised bed unit in Korea, designed by the Korean Institute of Energy Research with KEPCO. This plant uses solid potassium bicarbonate sorbent, which is low cost, but the higher generation temperatures mean that an alternative may be sought. A smaller pilot has also been operated by US company ADA using a sported amine. The general challenge of these fluidised bed reactors is that the sorbent must be of suitable density for fluidisation and sufficient mechanical stability to prevent excessive attrition and loss of material. A notable variant on solid sorbent processes is calcium looping, which exploits the carbonation reaction between calcium oxide and CO2 to form calcium carbonate. As reversing this reaction requires very high temperatures of over 900 degrees, the desorption reactor is usually heated by the in-situ combustion of more coal, using an Oxyfuel atmosphere to avoid contaminating the released CO2. This reactor raises its own steam and effectively acts as an additional Oxyfuel CFB power plant, retaining the energy released in carbonation and enabling very low energy penalties to be achieved. 2 EU-funded research consortiums are focused on developing calcium looping. The Cowling project, which commissioned a 1.7 megawatt thermal pilot at La Pareda in Spain, and the more recent Scarlet project, which uses an existing 1 megawatt thermal unit at the University of Darmstadt in Germany. With efficiency penalties as low as 2.8 percentage points calculated, the technology is thought to be capable of a capture cost of $20 to $25 per tonne of CO2. Other major advantages are the low cost of the sorbent and the potential for the waste material to be used in the cement industry. So membranes represent a completely different gas separation technology based on the differing rates of permeation of gases through a barrier, which is usually made from a polymer material. A membrane-based capture plant would be a relatively simple modular system with no chemical waste or steam extraction from the power plant. However, the driving force for membrane-based processes is usually provided by vacuum pumping of the permeate side. which quickly becomes energetically unfeasible for large pressure differences, and means that high CO2 purity and capture rates are not simultaneously achievable with a single separation. Furthermore, whilst many polymers permeate CO2 more easily than nitrogen, identifying a material which is sufficiently permeable and selective for the demanding requirements of carbon capture is quite challenging. So US company Membrane Technologies Research are one of the leading developers of membrane-based post-combustion capture technology, primarily under a program funded by the US Department of Energy. Using a highly permeable proprietary membrane, they have proposed a two-stage separation in which, instead of vacuum pumping, the second stage is driven by passing combustion air over the permeate side. This enriches the combustion air with CO2, in turn producing CO2-rich flue gases and enhancing the performance of the first membrane stage, which then removes CO2 for sequestration. The company have tried a 1 megawatt skid of this process at the US National Carbon Capture Facility and plan further scale up if funding allows. Like most membrane processes, the technology is most effective at partial capture rates, but is estimated to be capable of $45 per tonne at 90% capture. A great deal of academic research has been conducted on developing highly advanced membrane materials which are more selective or permeable to CO2, typically using amine functionalized polymers or embedding inorganic particles known as mixed matrix membranes. An EU project successfully trialled a polyvinyl amine-based membrane on real coal plant flue gases in Portugal. Other interesting concepts include membranes which support a CO2 selective solvent such as ionic liquid. However, as the selectivity of the CO2 separation process is primarily limited by the low pressure difference across the membrane, increasing the selectivity beyond a certain point yields diminishing returns. Mixed matrix membranes may be of interest for producing more permeable membranes, which would lead to reduced surface area required for the process. So another idea is low temperature separation, otherwise known as cryogenic separation. Concentrations found in typical flue gas, CO2 will start to desublimate, that is solidify, if cooled to below minus 100 degrees, with around minus 120 degrees required to achieve 90% capture. Although refrigerating flue gas to these temperatures can be energetically demanding, several studies have indicated that such a process could compete with solvent-based capture. The cryogenic CO2 capture technology from Sustainable Energy Solutions cools flue gases by direct contact with a cryogenic liquid in a staged column, removing the resulting solid CO2 by filtration. Following bench scale tests, the company estimate as little as 0.74 gigajoules of electrical energy would be required per tonne of CO2 for a full-scale plant. So, turning to pre-combustion capture, this is associated with integrated gasification combined cycle, or IGCC power plants, which coal is first gasified to CO and hydrogen prior to combustion in a gas turbine. Only a handful of such power plants have ever been built, but a few projects currently under construction have resurrected the technology with a view to implementing carbon capture. As syngas is at much higher pressures and has higher CO2 concentrations than flue gas, CO2 removal is in principle much easier and should be well suited to pressure-driven systems such as sorbents and membranes. However, the capture process involves several gas processing steps and contains inefficiencies and energy penalties throughout, including the steam required for the water-gas shift reaction for converting CO to CO2, and the need to cool the syngas prior to the capture solvent. Most research aims to carry out all these steps at warm syngas temperatures so that the heat and water content can be retained in the hydrogen-rich gas fed to the turbine. In particular, the CO2 capture step could be integrated into the same reactor as the water-gas shift. So known as sorbent-enhanced water-gas shift, adding CO2 sorbents to the water-gas shift reactor helps drive the equilibrium of the reaction to completion, potentially saving on steam use as well as the capital expense of several reactors. A notable project in this field is the EU project CESAR, led by the Energy Research Centre of the Netherlands, which develops a pressure swing process using a clay-like sorbent called hydrotalcite, and claims full-scale capture costs as low as $25 per tonne. Having successfully tested technology at a small pilot scale, is being further scaled up as part of another EU project for use with blast furnaces rather than power plants. So hydrogen is a small molecule which is relatively easy to separate from shifted syngas using membranes, and a wide range of materials can therefore be used. Polymers are cheap and easy to process, but have limited stability at warm syngas temperatures. Again, MTR have also developed a proprietary membrane for pre-combustion applications, which is stable at 200 degrees and is being tested at the scale of 1 tonne of CO2 per day. More interest, however, is focused on membranes from porous inorganic materials and precious metals, which can operate at high enough temperatures to be integrated with the water-gas shift reaction. Analogously to sorbent-enhanced water-gas shift, these membrane reactors would also remove CO2 from the reactor as it is produced. So far, only small-scale tests have been conducted using this concept, but capture costs below $30 per tonne are thought to be achievable. The principle of oxyfuel combustion is to fire coal in oxygen rather than air, producing flue gases consisting mainly of CO2 and water, from which the CO2 can be purified relatively easily. Conventional oxyfuel usually also recycles flue gas to the boiler to mimic the temperatures and heat transfer rates typical of air combustion. However, oxyfuel research has largely aimed to exploit the properties of oxyfuel combustion in novel, higher efficiency power generation systems, which can offset the considerable energy penalty of oxygen production. For the oxygen production itself, work is being done on membrane systems, which could potentially offer an alternative to commercial cryogenic air separation units, but these are currently far from the necessary scale. The most widely investigated approach is to carry out oxyfuel combustion at high pressures, which enables the significant latent heat of water vaporization in the flue gases to be recovered as useful work, along with other benefits including smaller equipment, reduced air ingress and improved heat transfer. Early development of this idea by Italian companies Enel and IEACCC led to a small pilot being commissioned in 2007, operating at 10 bar. A more advanced concept with minimal flue gas recyclers being conceived by Washington University, using several connected furnace stages to which fuel is added incrementally. A scaled-up version of this process would be calculated to have an efficiency penalty below 4 percentage points, but only a small combustor pilot has so far been trialled. The principle of oxyfuel combustion can also be applied to gas turbines, with a number of different designs having been developed primarily for natural gas. However, these concepts can equally be applied to coal-derived syngas as a potential alternative to the more established combination of an IGCC plant with pre-combustion capture. US companies Clean Energy Systems and 8 Rivers Capital have both developed novel designs for an oxyfuel gas turbine cycle, which they're currently scaling up. For further details, a recent webinar on this topic has been produced by the IEA Greenhouse Gas Programme. It's available from their website. The alum cycle process from 8 Rivers Capital is particularly noteworthy, as even with coal gasification accounted for, is estimated to be capable of higher efficiencies and lower electricity costs than a conventional coal plant without CO2 capture. Syngas and oxygen are combusted at 300 bar to produce an exhaust of supercritical CO2 and steam, which can be used to drive a highly efficient and compact turbine. Under the portfolio company Net Power, the process is currently being scaled up to 50 megawatt thermal natural gas pilot in La Porte, Texas. So lastly, chemical looping combustion is a unique approach to carbon capture which avoids any gas separation process and is therefore theoretically capable of achieving very low energy penalties, which should be mainly associated with CO2 compression. It can be thought of as a variant of oxyfuel combustion without the need for costly air separation, in which oxygen is delivered to the fuel by a solid oxide, known as the carrier material. The process uses two interconnected reactors, which are usually fluidized beds, which circulate the carrier material between the fuel and an air reactor, which regenerates the oxide. As solid-solid reactions are much too slow, chemical looping combustion of coal requires in-situ gasification with fluidizing steam or CO2. The inevitable loss of oxygen carrier with ash removal also means that low-cost carriers are necessary for a coal-based power plant. So two largely US-based projects have made the most progress with chemical looping combustion for coal. Alstom, now GE Power, have commissioned the largest pilot 3 megawatts thermal using interconnected fluidized beds and a carrier based on calcium sulfate, which is itself generated in situ from limestone and the sulfur in the coal. With an estimated full-scale efficiency approaching 36% higher heating value, the company aims to scale the process up to a 50 megawatt pilot by 2020. Babcock and Wilcox, meanwhile, developed a relatively compact process based on countercurrent moving bed reactors and uses iron oxide as a low-cost carrier material. This has so far been tested in a small pilot. So to conclude, CTS is a commercial process which has been successfully demonstrated on coal power plant, but remains prohibitively expensive in all but the most economically favourable scenarios. Research efforts worldwide have therefore sought to develop new CO2 capture technologies which can deliver lower costs than the established first-generation technologies such as amine-based capture. Many of these technologies show the potential to deliver a cost of capture of $30 per tonne of CO2, with some even going beyond this. New coal plants with carbon capture should exploit power generation technologies which inherently incorporate CO2 capture in their design, with chemical looping and the integrated gasification alum cycle appearing most capable of achieving a step change reduction in costs. These technologies are both currently being scaled up to large pilots and could see full-scale demonstration within the decade. For existing coal plant, retrofit of some form of post-combustion capture will still be necessary. Whilst numerous solvent systems have been developed, steady progress in commercial amine solvents means that it will be challenging for more complex processes to enter the market without significant gains. With its potential to use low-grade heat for regeneration, enzyme-activated solvents may be able to achieve this. Solid sorbents may have even greater potential to reduce the energy penalty and cost, but many high-performance materials are too costly, and scale up to large reactors could be challenging. Structured beds based on simple materials could be a low-cost route. Membranes offer several operational advantages, but are unlikely to be very competitive at high capture rates. Real gains may be possible, however, where the retrofitted capture plant generates its own power, as for calcium looping or fuel cell-based systems, although this additional power may not always be desirable. So I'll just close with some overall perspective on the direction of carbon capture research. Although much academic research in particular is focused on developing quite complex high-performance materials, there is a growing tendency towards lower-cost material systems which are less vulnerable to contamination and costly to replace. In the past, many research programs have targeted very high capture rates which are well suited to existing amine technologies. Given that several national regulations now require coal plant only to meet CO2 emission levels equivalent to that of gas turbine plant, technologies suited to lower capture rates, such as membranes and sorbents, should be considered and further investigated on this basis. Ultimately, the huge variety of site-specific factors associated with existing coal plants will mean that there may not be a single winner from these emerging technologies, and a range of solutions should cater for different circumstances. Finally, it should be noted that the cost of commercial amine technologies is projected to fall as more demonstration plants lead to operational optimization, risk reduction, and easier financing. However, the large energy penalty and accompanying increase in coal use associated with this technology will always present a barrier to government and public acceptance, so more efficient technologies should continue to be pursued. And I'd like to finish there, and I hope you send in some questions. The next webinar in May is called Emission Standards and Control of PM2.5 from Coal-Fired Power Plant. That will be given by Xinjiang. I think I'll pass you back to Debo.
Lovely. Thanks very much, Toby, for a really interesting presentation. I'm just going to have a look and see what questions have come in and give Toby a minute to think about the answers for them. Okay, we've got a few questions come in. First one, Toby. Thanks for an interesting talk. Do you think that public R&D funding is being effectively directed to look at novel technologies? Have you found issues of balance in this regard?
Thanks. Yeah, I think there's a lot of debate about how much research funding should go into really novel concepts and how much should focus on optimizing the systems we already have. I mean, I think the US program has a good approach, and they've really trying to fund as many novel ideas as possible while still progressing more developed concepts. But I mean, of course, a lot of these novel ideas won't ever take off. But I mean, I think there's always a value to ambitious research, and unfortunately, this kind of CCS research is declining in the EU in particular, where CCS is increasingly off the agenda. I mean, it's a difficult balance to achieve. Obviously, we still need to work on more developed technologies as well. But as I said in my final point, I think there's a huge psychological advantage to dramatically improving the efficiency of CCS with some new idea.
Thank you. Now, we'll go to this first question, which seems to be about storage, which isn't really the focus of this presentation, but I'll see if you've got any thoughts on it, Toby. The comment is that CO2 needs more storage space than was originally taken up by the coal which produced it. Excuse me. Is it realistic to suppose that we can find enough space for all that CO2? Well, I would say it's compressed, anyhow.
Yeah, slightly outside of my expertise, but I mean, yeah, the CO2 is highly compressed, and there's been extensive studies on the amount of pore space there is available for CO2 storage, and it seems as likely to be sufficient, at least, to provide enough CO2 storage for the our CCS requirements over the next century.
Yeah, I would add that at this stage, storage space isn't the main limiting factor. Okay, next question, Toby. Oh, there's lots coming in. Do the costs of CCS in terms of dollar per tonne of CO2 refer to dollar per tonne of CO2 captured or dollar per tonne of CO2 emissions avoided, taking account of the energy penalty?
Yeah, that's a good question. Most technologies quote their costs in terms of CO2 captured, as this generally looks better. In the report, there's more. This distinction is made more carefully, but I think in this presentation, all costs were per tonne of CO2 captured.
And the next question links in with that, Toby. It says, I'm sure the answer will vary with the technology, but for some of the leading techniques, how is the cost per tonne of capture split between the energy penalty versus the capital cost?
Yeah, another good question. I mean, it would definitely be interesting to know that for many novel technologies, particularly ones developed by private companies, you definitely can't obtain that information. Where it is obtainable, it's given in the report, but yeah, it's unfortunately quite rare to have that information. Although, given that you often have the energy penalty given as well, I suppose you can usually work out you could usually make a rough calculation of how much the cost is associated with that.
Okay, now we're on to the last question that's come in so far, Toby. It's about chemical looping, which has often been touted to be a very efficient option, but it seems that it has moved forward rather slowly, and we are only coming to small pilot scale now. Can chemical looping combustion development be speeded up somehow, and does it have the necessary champions to drive it forward?
Yeah, I think this is a quite a common view. I don't know if chemical looping has been developed that slowly. I mean, for carbon capture, it's only really got going at the beginning of the millennium, and compared to some other technologies, it's a fairly large scale now. I think Alstom Power in the US were a big champion of this technology, and I don't actually know whether that will be continuing now they've been bought by GE. I think it's a promising technology, and it should be pursued by them, but I don't know if the stance has changed on that. So yeah, we'll have to wait and see. Just to come back to the previous question, I think I should emphasise that for most established technologies, the energy penalty is by far the most significant cost in terms of how that, not so much in terms of additional fuel use, but it means you need a much bigger power plant, which is expensive. So yeah, I think that should be certainly taken into consideration.
Okay, that's all the questions. Thank you very much, Toby, and thanks to all our listeners. Just to say that Toby's PowerPoint will be available to download from our website from the webinar page of www.iea-coal.org later on today. And I hope you'll join us on Wednesday, 18th of May, for Zing's presentation on the emission standards and control of PM 2.5s from coal-fired power plant. Thanks very much. Have a good afternoon. Bye-bye.